Okay, Bio, welcome to your screencast on organic compounds. This will be the first of two screencasts on organic compounds, and it's going to be a lot of information coming at you pretty quick, so get your pencils ready. So, let's just get right to it. Okay, organic compounds. Why are they important to know and understand? Well, they're important to know and understand because all living things are made up of the exact same organic compounds. And you might be wondering why a picture of my puppy, the chrysalises in the bio, room in the KC, a picture of me as a small child, and a lobster are all up here. And it's because we are all composed of the exact same 4 types of organic compounds, but just in different ratios. Which is pretty incredible. So, let's talk about what is an organic compound. And it's going to be really important for you to note that organic compounds are not what you think of when you think of the grocery store. Now, these are organic fruits and vegetables, but USDA organic and organic as we refer to it in science class are not the same thing. And you shouldn't conflate the two. Whenever we talk about organic compounds in our class, it's going to be, we're referring to compounds that contain the element carbon. So let's get rid of the grocery store. Delete that. And instead let's throw a picture of carbon up here. Okay, here's a picture of carbon. So any compound that includes carbon is an organic compound. And carbon is a really great building block for biomolecules because it has 4 valence electrons, 1, 2, 3, 4, which means that it can make 4 bonds with surrounding molecules. I'm going to write that here, 4 bonds. And it can make long chains, either branched chains or linear. That's not how you spell linear. So, it can make branched or linear chains, which makes it a really flexible and useful building tool. So, organic compounds, compounds that contain carbon, not USDA organic. Okay, and overall, there are 4 major classes of organic compounds. The first class is carbohydrate. The next class is fats and lipids. The next is proteins. This is a T, not an I. And the last class is nucleic acid. We're just going to be talking about the first 2 today, carbohydrates and fats and lipids. So, when I say carbohydrate, undoubtedly you think about bread or pasta or potentially even potatoes. But carbohydrates are actually a very diverse group. So, yes, bread is composed of carbohydrate, but also so is the shell of our friend the lobster, and additionally, the majority of the trunk of this tree is also carbohydrate, and even a pile of sugar. These are all examples of carbohydrates. Okay, so let's talk about the functions of carbohydrates. The primary function, or no, not the primary function, but one of the functions of carbohydrates is energy. I'm sure you've heard of people carbo-loading before races. Carbohydrates are a good, quick source of energy. Another function is structure. So, carbohydrates are providing a structure both for the shell of this lobster and also for the trunk of this tree. It can be very rigid. And the last function of carbohydrates is cell signaling. So there will be branched chains of carbohydrates embedded on or within a cell membrane that they serve as a molecular flag of sorts. For example, red blood cells. Have you ever heard of being Rh positive or negative? Or even the blood types A, no, actually that's protein. But Rh positive or negative is a sugar complex that's either present on the red blood cell or not present on the red blood cell. So they're basically little flags that tell cells what type of cell they are. So overall, there you have it, carbohydrates. Let's talk about the different types of carbohydrate. So the most basic unit of a carbohydrate is called a monosaccharide. I'm going to write that down. Mono. It's a long word. Mono meaning one, and saccharide meaning sugar. One sugar. So a perfect example of a monosaccharide is glucose. A sugar I'm sure you've all heard of before. I'm going to throw up a picture of glucose here. Ah, look, it's a twofer. Glucose and fructose. So these are two different monosaccharides, glucose and fructose, and they can actually join together to form what's called a disaccharide. Or two sugars. And I'm sure you've heard of that sugar as well. The combination of glucose and fructose is called sucrose. I'm going to throw up a picture of that as well. So this is an example of sucrose. You can see in here, here's the glucose and here's the fructose, and they make common table sugar, sucrose. There's one more variety of carbohydrate that you should know, and that is polysaccharide. And as you might have guessed, a polysaccharide is going to be many sugars. Actually, I should probably put it down below here because we're going in order of smallest. There's two L's. Down to biggest. So a polysaccharide is many sugars all put together, and you've probably heard of a couple different polysaccharides. The first that you might have heard of is starch. You'd find starch in potatoes, for example. Another polysaccharide that you have just been introduced to but might not know well yet is chitin. Chitin is the sugar that composes the lobster shell. It's a polysaccharide. And the last is that you've probably heard of is cellulose. Oops. Cellulose is you probably heard of it. If you haven't heard of it, cellulose, then you've definitely heard of something called fiber. When we talk about eating a high fiber diet, you're eating a diet really high in cellulose. So the amazing thing about these three polysaccharides, which are so different, is that they're all composed of monomers of glucose. So all built from glucose. And what makes them different is how these glucose monomers are all stuck together. Starch is the only one of this list of three that's actually digestible by us. Both chitin and cellulose, we don't have the ability to break them down. We can't break the bonds that are in between the glucose monomers. But pretty incredible that all three are built from exactly the same building blocks, but have incredibly different structures and ultimately functions. Okay, So, poom. Is there anything else that I need to tell you about sugars? I don't think so. Monosaccharides. Oh man, I really should work on how these things are ordered. Biggest down here. Anyway, okay. Unimportant. Moving on to our next organic molecule, which is fats and lipids. So, fats and lipids, before we talk about the structure, let's talk about their different functions. Fats and lipids functions. I'm sure you've heard of fat as an energy storage molecule. And indeed, it is important in energy storage, but it's also what all cell membranes are composed of. And additionally, it's important in vitamin production and storage. And lastly, it composes all steroid hormones. If you don't know what steroid hormones are, then you definitely, even if you don't know what they are, you definitely feel their effects, especially right now because you're all teenagers. Testosterone and estrogen are both examples of steroid hormones, and those two hormones are composed of fat. Okay, so those are the functions of fats and lipids, and now let's talk a little bit about the structure. So fats and lipids are a little bit harder to organize than are carbohydrates, because carbohydrates have these great monomers, or monosaccharides, disaccharides, and polysaccharides. It's really easy to classify them. With fats and lipids, there isn't a single great monomer example because they're actually a very diverse group of organic molecules. But we're going to talk about two here today. The first one is called a fatty acid. And I'm going to throw up a picture of a fatty acid here. Okay, here's your picture of a fatty acid. You'll note here that there are two types of fatty acids. Well, first, overall, a fatty acid is basically just a long chain of carbon and hydrogen. And the energy of a fat is actually stored within the bonds between these carbon molecules. So the longer the chain, the more energy contained within the molecule. Okay, so overall, two different types of fatty acids. There's saturated fatty acids, which mean all the carbons are bonded to two hydrogens, or three. But every bond is a single bond between carbon and either another carbon or another element. An unsaturated fatty acid is a double bond between a carbon. We'll talk a little bit more later about what the saturated versus unsaturated, the implications of those things for the structure and the function of the fatty acids. But for right now, all you need to know is that there are saturated and unsaturated fatty acids, and that the difference is the number of bonds between the carbons. Okay, so this is a fatty acid. The other molecule that you need to become acquainted with is called glycerol. And actually, I'm going to move this over and shrink it down a little bit and put glycerol right here. And I'm going to throw up a picture of a glycerol for you. Okay, here is a picture of a glycerol. Note, it's important to note that there are 3 molecules of carbon in a row, and each one is bound to an OH group. It's also called a hydroxyl or an alcohol group. So glycerol is composed of a carbon chain and then some alcohol groups. Okay, so fatty acids and glycerols both combine to form the two different lipids that we are going to focus on today. And the first one is called... Oh, before I move on, there's something I forgot to tell you about fatty acids. They hate water. They're very hydrophobic. Oops. Water fearing. And you probably all know this from experience. If you ever made salad dressing before, the oil and the vinegar separate. Well, the vinegar is a water-based substance, and the oil is a fat. It's hydrophobic, hates water. Okay, so, moving on. First fat molecule that we're going to be talking about is a triglyceride. Oops, it's not TRY, it's TRI. Triglyceride, the main, you know these, you know and probably love them because triglycerides compose things like butter, olive oil, and the fat that's in your steak. So, very tasty. The main functions of triglycerides, as you might have guessed, is energy storage. And I'm just going to toss up a quick image of a triglyceride for you now. Okay, note well. Here is your glycerol head. The OH groups go and bond with these long fatty acid chains right here. So the structures that we saw before, fatty acids, saturated fatty acids, and glycerol come together to form this triglyceride. Tri meaning three. So there are three tails, 1, 2, 3, and a head. This is an unsaturated, sorry, that was wrong. It's a saturated triglyceride because all the bonds are single bonds. Saturated fatty acid tails. Okay, there you go. Triglyceride. There you have it. Okay, the next and actually last organic molecule that we're going to talk about today is a phospholipid. Now, the main function of a phospholipid is composing the cell membrane. I'm going to shrink these down. Give myself a little more space. Okay, phospholipids compose the cell membrane. I'm going to give you a picture. Okay, so I want you to ignore this and just focus on this structure here. So, zooming in on this phospholipid, you'll note we have our glycerol head right here. We have got two fatty acid tails, 1, 2. One is completely saturated, no double bonds, and one is unsaturated, it has a double bond. But unlike a triglyceride, which has 3 tails, triglyceride, a phospholipid only has 2 fatty acid tails, and it has a phosphate group up here. Now, this gives the molecule really interesting characteristic because, as you know, fatty acids are hydrophobic. It's a D. They hate water. And phosphate groups are actually hydrophilic. Here you can see the phosphate. The phosphate is right here. So this is hydrophilic here. Hydro. Which means it loves water. So this molecule is what's called biphasic. It has 2 phases. It has a water-loving part and a water-hating part. And the really interesting thing about this structure is that when you toss a group of phospholipids into a water-like solution, they will spontaneously form into a cell-like structure where the hydrophilic parts of the molecule touch the water and the hydrophobic parts of the molecule touch themselves. And I'm going to give you an image that will hopefully make this a little bit more clear. Throw it up here. So, this is what's spontaneously formed. A cell-like structure, which is composed of a lipid bilayer. So if we zoom way in on here you can see that this tiny little thing, this guy right here, is a phospholipid. That structure right here. The little ball here symbolizes the phosphate, and the little wiggly chains symbolize the fatty acid tails. Now it forms a bilayer, so the fatty acid tails of one touch the fatty acid tails of the other, and we have aqueous solution, meaning a water solution, both on the outside of this cell-like structure and on the inside of the cell-like structure, touching the phosphate heads. So, this is going to be really important later on as we move into our discussion of cellular life to understand why and how this happens, and the reason is because we've got this biphasic nature of our phospholipid, both the hydrophilic and the hydrophobic parts of the molecule. Okay, so I think this is it when it comes to fats and lipids. This is kind of a long screencast, and there's a lot of information in here. I trust you guys can handle it, though. Okay, I will see you all in class Monday, I believe. Or that might be wrong. Yeah, no, it's Monday. Okay, pause.